Okay, folks, so here we are. It is section 3.15 talking about doing this linear regression thing with our basis of features, but when we have multiple outputs. Now it's quite a short section, and there isn't actually that much really going on in it, and it's really quite just like algebraic and like just manipulations. But I think it's still useful to go through for practice, and there's actually a really he kind of mentions in passing something at the very end, which I just didn't really notice the first time around when we were going through it. And I thought it was actually a really cool, simple observation that I'm sure will be very useful. Okay, so what are we going to what are we talking about in this section? It's look, we have more than one target variable. So far we've been talking about just like a single y, and we had there's one target variable, but we had like multiple observations, and we're trying to figure out a single weight vector. And now we're in a setting where we have like k observations, and we're going to put them stack them in some vector. And now the question is, well, how does that affect our inference process? And the way he's going to talk about it, he's going to talk about it first in the case where our covariance structure is really simple, and the solution is really easy. But then the remarkable thing, which he kind of touches on at the end, is that, well, even if we have kind of more complicated covariance, the answer is still the same, because this amazing property that the maximum likelihood solution for the Gaussian has that is independent of the covariance. So it turns out that for the Gaussian, which is what we're going to consider here, it doesn't really matter. You can use more complicated covariance structures, but your estimate will have the very same simple form as you normally would if you just had kind of this spherical or a spherical shape where variance is the same in all directions. So that's kind of a pretty cool thing. Yeah, so let's just get into it. I think it's just going to be a bunch of, it should be pretty straightforward. It's just going to be a bunch of, algebra that we'll have to do. Okay, so let's read. So we have considered the case of a single target variable, and in some applications, and this is lots of applications, we may wish to predict k is greater than one target variable at the same time from kind of the same set of features applied to our x's. So which we denote collectively by the target vector t. So that t now is going to be, can you see this? Well, just about. So it's going to be, t1 to tk. And we're going to have to be careful in this section, because now we're going to have indices for time, or well, I guess for observations, and also indices for the different variables, so kind of the different elements of the output vector that we're trying to predict. So just something, just more bookkeeping for us to do. Okay. Now what does he say? So this could be done by introducing a different set of basis functions for each component of t, leading to multiple independent regression problems. So the idea is like, okay, well, just treat it as k independent problems. You can have custom features. That might be something you want to do. But what we're going to talk about here is actually kind of a simpler case. And the more common approach is to use the same set of basis functions to model all of the components of the target vector. So let's just highlight some of these things. So the same set of basis functions to model all of the components. Okay, and that looks like this picture here. Let's kind of highlight that. And so what's going on inside? If we unpack, what's happening in here is that we basically have this is going to be equal to, now there's kind of a W1 transpose times the features, all the way to WK transpose times, it's the same. So don't get confused. So previously we were working with, we saw something that looked like this before, but that was where the weight vector was the same, and we're dot producting it with the features evaluated for on each of the different observations. So there was like this W. So the W was just, there was no 1 on it. It was just W, and then but the X's had like I think it was like x1 to xn or whatever it was. So here, this is for like a single observation. We still are going to get k outputs, and we're going to compute those outputs by projecting the features for the input onto k different weight vectors. And so obviously the game is going to be, how do we figure out what those weight vectors are? Okay, and I might write this at some point. Yeah, so let's just make sure. So y is a k-dimensional column vector. W is an m by k matrix of parameters. Okay, so So W is, so it is k columns. So this is m by k. And notice what's happening. So now we're transposing it. So now those m rows become m columns. They're going to be projected onto the features, and then we're going to get k outputs out. Okay, yeah, we just have to be quite careful in this section just with all the bookkeeping. And phi x is an m-dimensional column vector with elements phi jx with phi 0x equals 1 as before. So phi hasn't changed. It's just, you know, our basis, our feature vector. And x comes in, we generate a bunch of features, m features, and now we're trying to figure out w. Okay, so now we're going to do, you know, we're going to play a simple game. Suppose we take the conditional distribution of the target vector to be an isotropic Gaussian of the form. Isotropic just means has the same variance. You know, if there's kind of the contour has the same variance in every direction. In that case, in our case, the variance is going to be 1 over beta. And this is kind of the simplest case. You should always start with this case first when you're trying to understand what's going on. Okay, so now notice, but we're dealing with a multivariate Gaussian, right? It's got k dimensions, 1 for each of the outputs that we're predicting. And we're going to predict the mean to have this form. It's going to have this, you know, our predicted mean. And the variance is the same in all directions. So in this kind of setting, you actually do have, you actually have k independent problems, because these weights are just going to, each row of W transpose is just going to be involved in explaining one of the elements of T. So maybe we can kind of expand this out a bit. Okay. So if we do that, you've got, you know, so this is what is this going to look like? So this is proportional to the exponential of minus, you know, t minus, I'm just going to call this y. And maybe there's a beta over 2, something like that. And so let's just look at what these t minus y's look like. That's gonna be the most important thing. So, and these are all vectors. So t minus y is gonna equal to t minus, let's just do it in 2 steps. W transpose phi, which is gonna be t minus, actually let's expand this guy out too. So it's going to be T1 to Tk minus W1 transpose phi all the way to Wk transpose phi. Right? And this is all kind of happening inside. And so what we do is we're just going to compute these differences, sum them up, all of that. And so this exponential is just going to be, you know, it's going to end up being equal to minus, I'm going to drop all the constants, but it'll be just T1 minus W1 transpose phi squared minus, you know, T2 minus, let's just erase all this, minus W2 transpose phi squared dot 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 dot. Well, this is just the same as then, you know, the exponential of each one of those terms multiplied, showing you that it's, and that's just a bunch of normal distributions, one for each element of T. So so basically in this setting, you essentially just have k, you have k independent problems you're dealing with, and for each one of those problems, you have a corresponding wk. So in the end, it's not going to be very surprising when you find out that the solution looks like exactly like what it did before. It's just that, and the phi's are exactly as we just have one set of phi's, but the t's are going to be those column vectors we formed. Now be careful here, this time for one of the outputs, one of the targets, but for all time. So it's exactly the same as before, except, you know, previously we didn't have a k index. We just had this like single target. Well, now you have k targets. So you have you remember those long vectors that were living in, like, when we were talking about the geometry of least squares, where there was one element for each observation. Okay, so now we have one of those long vectors for every single output. But the way we compute the solution is exactly the same, because essentially all we have here is k parallel problems. Okay, so that's kind of the big picture, but let's kind of go into it and see, just kind of work it out. Again, it's good practice for to work out the algebra of all these things. Okay, So you guys can see, very good. We can combine these into a matrix T of size n by k such that the nth row is given by Tn transpose. So let's just draw that out. So T is going to be T1 transpose all the way to Tn transpose, and this is k columns and n. So we have one row per observation. Similarly, and again, look, the order of these things doesn't really matter. It just depends on kind of your preference. You can kind of have it the other way around too, but you just have to make sure that the rows and columns all line up. So hopefully that's pretty obvious. Okay. Right. Similarly, we can combine the input vectors x1 to xn into a matrix X, which it's not really going to come up, but it's just kind of so we don't have to keep writing out x1 to xn. We don't have to keep conditioning on x1 to xn. We can just pack them all into x and just condition on that. The log likelihood function is then given by, so again, we've got this sum happening because we have n independent observations. Each one of those observations has a target, which is this k-dimensional thing. So this is actually, a k-dimensional vector. And we've got our features for that input being computed. And we've got W. And notice that W is the same, of course, across all the observations, just like it was before. But now just W happens to be this big matrix. So that might be a little bit scarier than before. But again, it's not going to be a big problem. Okay, so now we're going to get. So if we actually map this out, we kind of expand this, the exponential. We get terms like this, and this notation. Remember, you probably know this by now, but it just means the sum of the squares. So we've got two vectors, just their squared length. So this is going to be equal to sum on k Tn k minus, let's just call this yn k squared. So nothing too scary. Okay, so what we're going to do next is we're going to use our skills of differentiating with respect to matrices to actually just solve this equation for W directly. But before we do that, I again just want to emphasize that we should expect the answer to be, given the form that it has, we should expect the answer to just look like exactly what we had before, but having the rows or columns, whatever it is of W, being corresponding to one of the target variables. So just like kind of the scalar case before, we just have k scalar problems, and our solution should just look like exactly like what we had in that scalar setting, just plugging in the targets for that output channel. So that's kind of what we expect to find. But let's go and try to let's just derive the solution, and then we'll have a look at it. Okay, so right, so so we're just gonna call this L, and let me make sure you guys can see. Okay, yeah, okay, more or less. Okay, so I'm just gonna call this L, and it's just gonna be a function of, as far as we're concerned, it's just gonna be a function of W. So we're just gonna figure out what the gradient is. Okay, so this bit there's no W's in it, so we're just gonna ignore that. So we're just gonna write this as the minus beta over 2 times the sum on n. And remember, when we're doing these things, it's helpful to write things out as transposes. Sorry, as scalar products. So we'll see. Okay, you'll just see what I mean. So I've just written this equivalently, right? So this has just become that. Okay, maybe not quite up to the sum, but okay. All right, so now what we're gonna do is we're gonna play our normal game. We're gonna compute the differential. So how much does L change when W changes? So dl, you guys can see this, terrific, is going to be well, it's gonna be minus b over 2 times the sum on n. And I know because I've got the same thing transposing itself, there's going to be times a factor of 2 times Tn minus Wt phi xn transpose, and then there is a minus 1 times the dwt phi of xn. Okay, so our differential ended up in there, so let's just get rid of some of the constants. So we're going to end up getting a sum on b. So the beta minus the beta over half becomes just beta because there's a minus 1 and a 2. So we've got t of n minus wt phi. I'll just call it phi of n transpose dwt phi of xn. I think that's right. Okay. And now you might remember that the way it works with matrices is that you essentially just get you get this transpose times that transposed. So the gradient with respect to wt is going to be beta times the sum on n of tn minus wt phi n, no transpose because of the transpose here, so we got rid of that, times phi of xn transpose. Okay? So that is pretty good. We might want the gradient with respect to, we're going to want the gradient with respect to w, not w transpose, so let's just transpose this thing again. So then this is going to be beta times sum on n times phi xn, some t minus wt phi transpose. Right? Very good. Okay. And so now we just set this to 0. So we set this to 0. And so we get, and the beta disappears. So now we get on one side the sum on n phi xn times t of n. Now we just have to be careful because these t of n's are actually, each one of them is it's actually a vector. So I'm going to just to emphasize that. And now is going to equal to the sum on n on phi of n transpose w. Okay? So now what's the very next step? So again, we go back to that, oh, I'm sorry, this should be, I believe this should be transpose, yeah. Okay. Right. So now remember, we go back to that very useful pattern that we had before, that if you see something like a b transpose, like a n b n transpose, well, this is the same as you're actually evaluating a product, right? Where it's, where a is going to be, yeah, I don't know how you want to call it, but a, it's going to be a1 is going to be on the rows, and b is going to be on the, sorry, so a1 is going to be the columns of this A matrix, and b1, these transposes are going to be the rows of this matrix. So we just use that same, insight here and here. So we just apply it there. So I believe the way we define the big, remember there's this big phi matrix, right, which had like, however it looked like, it turned out that this phi of n transpose in terms of that big matrix was just going to equal to, this was actually just phi transpose phi times w. So this is now a big phi matrix. This looks like, this thing we have here looks like the matrix where each column would be a single observation. So if that is the transpose, then that means that each row was a single observation, and the columns were the features. So yeah, so this is our features matrix. So you go back and you'll see what the definition is there. Very good. And then we can apply the same thing onto the left side, and we just see that this is just phi of t times this big matrix T, where we pack all of our which we already described here. So we combine these into the matrix T of size nk. So that's all it is. And then all you do is you just say, well, then W is equal to phi t phi -1 times WT t, which is exactly this expression here. So that's all there is to it. So it's just a little bit of algebra, and you get the same answer. But if you'd forgotten how, what was going on with how to differentiate matrices, well, in this particular case, you would have actually been okay, because you could just recognize that, well, this is just k independent problems. And so if we actually unpack this, like what's actually, let's just call this thing, we'll just call this h on the left. So this is going to be equal to, let's say, h times t. And well, what is t? Well, h times t is just, it's t1 all the way to tk. And these are those long vectors again, where there's n rows, one for each observation, and you've got k columns, one for each kind of output channel. So you essentially just have you just have k independent parallel problems that you've, with the matrix algebra, you've managed to solve them all at once. But essentially, there's nothing new happening there. All right, so the summary of all that is that the solution to the regression problem could decouple between the different target variables. So we need to only compute a single pseudo-inverse matrix, which is shared by all the vectors wk. Okay, so that's kind of the cool thing there. Now, I think the really kind of the very interesting point that I hadn't noticed before. I mean, I would have just gone through here and just kind of churned it out, whatever the covariance was, get some answer, and you look at it, you're like, okay, great, that's the answer. But I think he actually points out this really interesting thing, and we'll see where it comes up. And we saw it like back in 2.34, but it's great to see it again here. And it says, look, so obviously, we've been working here with beta. It's just some, our covariance that we've assumed is just very simple, the same in all directions. Well, what if it's not the same in all directions, right? What if our noise that we think is corrupting, our observations is actually, it actually has some other pattern of covariance? Does the problem get more complicated? So interestingly, with the Gaussian, it doesn't. So we again get this decoupling into k independent regression problem. I'm actually going to highlight that again. Now he says it's unsurprising, but for me it was actually very surprising to kind of, so I'm going to say unsurprising. It's very surprising actually, I mean, when you notice it. And so I'm glad he pointed it out, because the parameters W define only the mean of the Gaussian noise distribution. And we know that the maximum likelihood solution for the mean of a multivariate Gaussian is independent of the covariance. So first, let's just see how that comes up. But what would be the fastest way of showing you guys that? Okay. Yeah, so okay, I think the fastest way would be we just modify this derivation that we have. Okay, so let's just do that. So if this beta was, if instead of beta we were dealing with some general precision matrix, then we wouldn't have a term that's just as simple as this. You would actually have a lambda sitting in there. So this beta would go away, and it would be a lambda sitting in there. And that in principle could make things very complicated, because now it's going to link everything, all these terms to each other. And so there's going to be kind of a lambda sitting in here as well. And so now this gradient, so now our gradient is going to be lambda, because we're going to transpose, this is going to come out on the other side. So now there's a lambda here and a lambda sitting there. But now the cool thing is that, so we're going to get kind of this expression. Now we're going to assume that lambda is invertible, and if lambda is invertible, then when we set this equation equal to 0, we can just multiply both sides on the left by lambda minus 1. This disappears. The same way, essentially what we did with beta, we just divided by beta. We're going to divide by this matrix lambda. And again, all you end up with is just this same condition, as if your covariance was isotropic. So it's like this lambda actually doesn't matter as far as this estimation is concerned. And so that's kind of why this kind of precision, or the covariance, whichever you want to work with it. I think that's I think quite cool, and it's something that I would have just done as a matter of course. Okay, get rid of it. Oh, isn't that nice? But I think it's pretty cool, and so I've just shown you kind of algebraically, like manipulations, why that's the case. I try to think a little bit about why intuitively that's the case, and I think it's related to the fact that we're trying to estimate the mean. Remember? Okay, so let's erase. So I'm going to erase some of this. Just give us some room to write some stuff out. Okay, so let's say we have some kind of point cloud of points. Well, of course, the point cloud is composed of points, and it's kind of just sitting over there. Okay, and I've just drawn the contours, but it's the point cloud. So if you include the lambda, it's to compute your unless we're just going to focus on figuring out the mean of this thing, because that's where W comes in. So let's pretend that our problem is just to figure out what is the mean of this point cloud, just given the points in it and assuming it's Gaussian. Well, okay, so having this lambda around, so what does lambda look like? Well, it's going to have some rotation times some kind of scaling times some other rotation. That's kind of if you apply SVD or do an eigen decomposition, whatever, that's what it tells you. So it tells you that, okay, well, you could minimize this thing by maybe rotating everything in some so that this point cloud becomes now aligned with one of these coordinate axes, expanding everything, rotating everything back, doing all that stuff. But if we actually look at this intuitively, we can see that, what would we do if the covariances were the same in every direction? Well, all we'd do is we would just kind of look at where the points are falling on the x-axis and look at where the points are falling on the y-axis, right? So if instead of if we had a round point cloud, which is kind of what we had in the previous case, and the radius was 1 over beta, that was the standard deviation. Well, all we do is we would just look at where the points are falling in either case. We'd say, well, that's the y-axis, that's the x-axis. Okay, there's our estimate of the mean. So now I think the reason why the covariance doesn't matter is that if we played the same game regardless of the covariance, we would still get the right answer. So intuitively, it's just been like, okay, well, let's just replace that with, and instead of trying to kind of line things up with like the way it's tilted, we just say forget it. We're just going to look at where just the point, we're just going to project the points onto the x-axis, project the points onto the y-axis, and just take the midpoints, wherever that crosses as the mean of our Gaussian. And it turns out that for the Gaussian, at least intuitively, that will always work. So you can pretend as if because it works for, it's independent of covariance, you can just pretend that you had a spherical covariance, so it's the same in all directions, and just do the simple thing that we do there. So you don't have to worry about the way the point cloud is shaped, the way it's pointed. You just figure out where the mean x value, the mean y value, and compute it that way, and it will work because of this property of the Gaussian. So so that's kind of what he's saying here, is that, look, you might think that this calculation, which we were doing for the covariance being spherical, is going to get way more complicated if our covariance now becomes funny shape. But it turns out that because of this nice property of the Gaussian, it doesn't. So it's quite remarkable. So I think it's a good thing to keep in mind, to just remember that at least for estimating the means for the Gaussian, we don't have to. It doesn't depend on the covariance. I actually I spent some time, and that's why it took a bit longer to make this video. Spent some time trying to find kind of easy examples of distributions where estimating the mean did depend on the variance. I think the closest that I got to kind of a reasonable one was the multivariate t distribution, and if you kind of look it up, I can't show it to you right now, but if you look it up, you'll see that things, once you have more than one data point, because of the way we essentially have the same term that we have here, but it's kind of showing up inside of it's being raised to some power, and then when we multiply, we take the logarithm, that power doesn't go away, so you still basically have a bunch of terms like this being raised to some power, and then maybe they'll interact funnily as you add the contributions of multiple points. But when I simulated it, it actually did look like there wasn't much of a difference. So even in my 2D cases, there wasn't a huge difference. So yeah, so I wasn't able to find a kind of a good example where they're really very different. I'm sure they exist. But anyway, the main thing to remember is that for the Gaussian, we can actually just estimate the mean as if this covariance was round, which is a pretty amazing property and a big time saver. So I think that's all I want to say about this section. I think it's yeah, it was pretty simple. Basically, just I think you can just kind of think about what's going on in the situation with k output channels, and you'll quickly realize that okay, your answers are going to be just the same, just k different answers, just like we had before. The really cool thing is, of course, this one that okay, that actually that same idea works when you are trying to even when you're the noise covariance, this noise cloud isn't round. When it has whatever shape, you can still just do the same thing. So I think it's pretty cool. He kind of just says, "Oh, it's really unsurprising," but I thought, when I read that, I was like, "Wow, that is actually pretty cool and pretty surprising to me, at least." So yeah, that's it. So let me know what you guys think. I hope you learned something. And next time, we're going to start on the very important topic of bias variance decomposition. I don't know if I'll do it as one video or two, but we'll get through it. It's really important and not very complicated. So it'll be a fun section, I think. So with that, I hope to see you in the next video. Bye.